Okay. All right. Good morning, everybody. We're going to be going through the topic 3 and also a little bit of paper 2, forces and work. Topic 8, 9. So have a quick look at the energy stores and systems. Now, it's really important to remember that an energy store does nothing. A store is just the ability to do work. When there's a transfer from one store to another store, that transfer is when an action happens. So that transfer could either be electrical work in a circuit, it could be a force moving something, it could be a heat transfer between two places, making one object colder and one object hotter, or it could be radiation through a vacuum, like the sun sending rays of light at 300 millimeters per second towards Earth. Now, the most common energy stores we encounter are chemical, kinetic, gravitational potential, and thermal. They sometimes mention elastic when it comes to things like bungee jumping. But remember, these are all stores. So chemical energy can't do anything. A fuel by itself cannot do anything. It requires a transfer, heating, for that fuel to be able to make something else warm. The force pathways, which I will call transfers from time to time, are mechanical pathways, mechanical transfers, when a force acts and an object moves. Remember that all forces always act in pairs. You can't find a force by itself ever. Electrical work, so this is when the electrical current flows. The electrons do work as they move through the circuit. Heating is when a temperature difference is induced or increased between two objects. And radiation, when a source and an absorber, so when there is a transfer of energy from a source to an absorber. So get it in your brain, chemical energy can't do anything, kinetic energy cannot do anything. However, forces can transfer energy from a chemical store to a kinetic store, making something happen. Energy is the ability to do work. Pathways cause work to be done. Gravitational potential energy. Remember, we call it potential energy because currently I'm sitting on the first floor, so I'm a couple of meters above the ground. But I'm not actually being pulled down. I'm not doing any work at the moment. I'm just sitting. I'm not doing any work while at school. But if I was to jump out the window, then the gravitational potential energy would be transferred through the force of gravity into kinetic energy, and I would fall. So the gravitational potential is the important bit. Not to be confused with gravity. Gravity is a force, and G is the force due to gravity. So it's newtons per kilogram. And we find G in the gravitational potential energy equation. Pardon me, G is not force due to gravity. G is gravitational field strength. We find G in the GPE equation. We also find G in weight is equal to mass times gravity when we're calculating the weight of an object. Stored energy can be released through a pathway or a transfer if the object's allowed to fall. So here's an example of a question that you might get with gravitational potential energy in it. Not in it as in Roadman, but in it as in there is gravitational potential energy mentioned in it. Moving objects of kinetic energy. So this is an example of a question that you might get with a long jumper using her kinetic energy. Kinetic energy is 1/2 times mass times v squared. Common mistake is to forget to square the v. And if you're writing a particular velocity in, so 1/2 times 46 times 8 squared, that's fine. But if you do this, 8 meters per second squared, then you've now given that as acceleration. Okay, so the unit is not squared. The unit of acceleration is meters per second squared. The units of, I don't know why that line has appeared, sorry. The units of speed are meters per second. A quick reminder as well that if I have got a gravitational potential energy store of 100 joules, if that object falls towards the ground, oh, oops, don't know why that happens, 100 joules, if that object falls towards the ground, then just as that object is about to touch the ground, at this point here, my object will have 100 joules of kinetic energy. So gravitational potential energy and kinetic energy are interchangeable. We assume 100% efficiency. Ooh. Okay, so we assume that there's no energy lost. In reality, there will be some energy that is transferred as waste to a thermal store in the surroundings. But when we get any questions about this, then we just have to assume 100% efficiency. So a question that was asked was something along the lines of this. There is a cliff, and on top of the cliff there is a rock, and this rock has got 100 joules of gravitational potential energy. What velocity was the rock going at the bottom of the cliff? Well, the question I get a lot of the time is, we've got GPE here. How are we going to work out kinetic energy? Where's the kinetic energy? What's the equation for GPE and velocity? And the answer is there is none. But the 100 joules of gravitational potential energy will be transferred into a kinetic store of 100 joules by gravity. So we can use kinetic energy equation, EK equals 1/2 times m times v squared. Rearrange that to find kinetic energy. And as long as we know the mass of the rock, we can figure out the velocity of the rock at the bottom. Just something to bear in mind, okay? So especially if you're looking at higher tier papers, they like to include that because it confuses people. But it won't confuse you anymore. An energy system is a group of objects that have the ability to do work. A closed energy system is a system where there's no extra energy going in or coming out. Energy cannot be created or destroyed. So when work is done, energy from one store is carried along a pathway to another energy store. So here's an energy flow diagram for an electric shaver. The battery inside the shaver has got a store of chemical energy. The current that flows from the battery to the blades is moving through an electrical pathway. So the energy is flowing, the energy is being transferred through an electrical pathway. Energy from the motor follows a mechanical pathway, which means that there's forces causing my motor to turn. Not just one motor, there are of course 3 motors in this little shaver. Into a kinetic store in the blades. As the blades are vibrating, there is friction in between the mechanisms of this motor, causing an increase in the thermal energy store. There's also radiation. There's no such thing as a sound store, pardon me. There's a sound radiation pathway. So the sound is being radiated to the environment. Now, sound will always radiate and increase the thermal energy store as well. Me just sitting in my room right now talking, I've increased the thermal store of the air around me because there's been a radiation pathway through sound from me to the environment. Here's some examples of an energy change in a system. You have to know these. An object thrown or projected upwards. You've got to be able to talk about the stores and also the transfers. And another one. For 10 seconds, you can pause and have a read. Oh, sound transfer, pardon me. And another one for 10 seconds. Another. Again, you'll hear a sound. It is not sound energy. It is a transfer. And water boiling in a system. In a kettle, pardon. Okay, here's some questions for 10 seconds each. Pause them and have a go. and your answers. Okay, energy cannot be created or destroyed. It can be dissipated, and that just means wasted. And it can be transferred, and that means moved from one store into another one. Dissipation is a wasted transfer. In a closed energy system, a system wherein there is no energy going inside or outside, there is no change to the total energy in the system, there can be a transfer of energy, but not of mass. So energy into a closed system will equal the energy out. The diagram on the right is a Sankey diagram. Shows you the energy transfer for a light bulb. All the energy stored can be accounted for as light energy and thermal energy. Again, light isn't really an energy; it's a transfer. But the Sankey diagram shows that the electrical transfer that's going into the system gives 10% of a light transfer, which is useful, and 90% into the thermal energy stored by heating, which is unuseful. Now, just like when you go for a number 2, and it sounds like poo, the poo goes down into the toilet. And I know this is icky, but there you go. It's how we're going to remember it. In a Sankey diagram, the waste always goes down. So whatever diagram you've got, it doesn't matter. As long as the arrow is going down, then that is the waste. I know, ooh. Unwanted energy transfers, waste energy transfers, result in energy stores that are not useful. So there's a Formula 1 car below, and eventually all the chemical energy of the fuel put in ends up as unwanted thermal energy, which is dissipated to the surroundings. Unwanted energy is often described as being wasted. So chemical energy stored in the fuel is transferred to a kinetic store, which is very useful, but eventually that will also wind up turning into thermal energy, either through drag transferring energy from the kinetic store to thermal energy in the air, or friction transferring energy from the kinetic energy store to thermal store in the tarmac. The chemical energy is also transferred through this is turned into a sound transfer, which will increase the thermal energy of the surroundings. And the car just gets hot. I mean, the engine gets hot, the wheels get hot, everything gets hot, which will eventually dissipate into the environment through a heating transfer. Now, to reduce unwanted energy transfers, we use oil as a lubricant, and all that lubricants do is separate surfaces so that they can't come into contact and therefore reduce friction. The more you reduce friction, then the less wasted heat there will be. Thermal insulation can also be used to reduce unwanted energy transfers. If I have got a source of energy and an absorber of energy, if there is a straight transfer between these two, insulation is a blocker. So insulation reduces the amount of energy that is transferring to object B. So this is the amount of energy on the right-hand side here, the amount of energy that is lost in a building and all the different parts. Higher thermal conductivity. Thermal and heat conductivity, to conduct is to allow something to pass through. So the higher the amount of heat that's able to pass through something, the quicker the heat is transferred through a material. Concrete has got a very high thermal conductivity. Air has got a very low thermal conductivity. So we use insulation as ways of reducing the amount of conductivity that occurs. Insulation is just little pockets of air trapped in some kind of material. Think about bubble wrap. Fiberglass, you can get loads and loads of fiberglass. It not only traps air, but also has a very low conductivity. Foam doesn't have itself, the foam itself, isn't actually very insulative. However, the air that is trapped in between is very insulative. And trapped gas is in double glazing, so the air that is in the gap between two pieces of so double glazing works by having one piece of glass and another piece of glass with air in between. Now, glass lets heat through very, very quickly. So if I just had a single pane of glass, the heat would get through straight away. But because I've got two panes of glass with air in between, the air absorbs some of that heat and less heat will get through. We can calculate the efficiency of an object by looking at the total useful energy that is transferred and dividing that by the total energy supplied to the device. Efficiency is useful divided by total. And if you don't know the way of remembering that, then come and speak to me, because I'm not going to put it on. I don't want it to. I don't want to share it with my competitors. It's very clever. Efficiency is usually given as a number between 0 and 1. You cannot get something which is 1.1 efficient, because that implies that it's 110% efficient. We can't do that because of the law of conservation of energy. Energy can either be created nor destroyed, but only transfers from one form into another. We can find efficiency of the energy transferred by the device, and that can either be given in joules for energy or in watts for power. If you want to turn a decimal efficiency into a percentage efficiency, multiply it by 100. So 0.24 is the same as 24% efficiency. The only trick is figuring out which energy store is the useful one. So sometimes you'll say something like, this is a drill. I'm going to draw a brilliant drill. Oh, that's actually not that bad. Okay. And the drill gives out 10 joules of kinetic energy. It gives out 2 joules of thermal energy, and it transfers at the same time eventually into the thermal energy 10 joules of sound as a transfer. Now, what is the useful energy here? What is the wasted energy here? The kinetic energy is useful because I want my drill bit to rotate. I don't want my mechanism to get hot. That's a waste. And I don't need it to be loud. That's also a waste. So what's the useful energy here? 10 joules. What's the wasted energy? 12 joules. What's the total energy? Add those two together, 22 joules. How do we reduce unwanted energy transfers? Now, no device can be 100% efficient, but we pay for the energy that we've got. We pay for the fuel, we pay for the electricity. So we want to reduce the amount of waste so that we don't lose money. To reduce friction, we're going to use a lubrication. So mechanical devices that use any kind of moving parts moving together or surfaces moving over each other can be made more efficient by lubrication. We don't always want to reduce friction. Friction can be quite useful, for example, in your brakes. Like, you wouldn't want to add lubrication to the brakes on your bicycle because your bike would be more difficult to stop. Sound radiation, when a hairdryer is being used, the quieter it is, then the less radiation, the less energy that is being wasted. We want to reduce the amount of energy that's being wasted through our electrical circuits, because as we know, when electrons collide with the positive nuclei in the ions of wires, then they transfer there's a transfer from the kinetic energy store of the electron to the thermal energy store of the positive ions in the wire, causing them to oscillate and vibrate more, increasing the thermal store of the wire. Remember that we need to know that for resistance. It's important, especially higher tier. It's something they talk about, something they ask questions about a lot. And whenever there's any kind of a heating effect, so if thermal energy is being lost, then we want to stop that as well. So mechanical devices can be made more efficient through lubrication, and having good insulation reduces the rate of thermal energy transfers, and that's good. Here are your questions. Another super secret password. If you come up to me today and you say keychain kitty cat oil, you shall get 10 achievement points. Actually, that's not fair. I shouldn't put that during the questions because you just pause them and skip them. Okay, never mind. Ignore that. I'm going to make up a new password. And here are your answers. Okay, work done. We know that energy transfers occur between one store into another store. Now, this transfer here can also be called the work done. Now, there's a specific calculation for the work done by a force over a specific distance. When a force causes an object to move through a distance, we can say that work is done on the object. So a force does work on an object when the force causes a displacement of the object. Work can be calculated using the equation. Work done is force times distance. Energy transferred, joule, is the same as work done, joule. It's also not, it can also be the total amount of energy stores. So energy stores are also measured in joules as well. Here's an example of what a question might look like. A box is pushed 3 meters across the floor with a force of 120 newtons. Work out the work done in the moving box. And force multiplied by distance. And if it's a box that's going up a slope like that, and we say that the slope is 12 meters long, but that there was an increase in height of 2 meters, 2 meters, then we use the 2 meters, not the 12 meters. Because yes, even though this object has gone up 12 meters of a slope, the work is being done against gravity. So if we've got a box in a slope, use the box going upwards because it's the work against gravity that we're looking at. Another example. Just like, yeah, this is the example of that. Sorry, I forgot to put this in. The escalator moves 50 meters horizontally and 8 meters vertically. Calculate the work done by the motor against gravity. We've got to use gravity. Now, the mass of this chappy in here, 70 kilograms. The way we work out gravity, what's up my G? Weight equals mass times gravity. And they may not give you G, so remember that G is 10. Here it is. Take G is equal to 10 newtons per kilogram. So got a chap going up an escalator. He's down here with 70 kilograms of mass. He goes up this 15-meter long escalator, but we're not actually going to use either one of those numbers. We're going to use the 8-meter vertical because we're doing work against gravity, and we have to work out the total amount of force required to move something that is 70 kilograms. 70 kilograms, the weight is 70 times 10, giving you 700 newtons, and that's the one that we use. Just a reminder that so we talked about this as well, and it's not a reminder, but this was a question that came up as well. We had I think again, it might have been a rock that was falling off the side of a cliff, and we were given the force, and we were given the total amount of energy, and we were asked to find the height of this object off the ground. Gravitational potential energy is equal to mass times gravity times height. Now, mass times gravity is also the same as weight. And a weight is a force. Now, a height is just a distance that goes upwards. Okay, so it's just the only thing different between a distance and height in our brains is that distance is along a horizontal axis and height is along a vertical axis. Weight, when I multiply mass and gravity together, it becomes weight. Weight is a force. A height is a distance. So force times distance will give you energy. Okay, so this equation, gravitational potential energy, is just the exact same as the work done equation, just with slightly different numbers that are interchangeable. So if let's say that this rock had a force of I think it was 2,700 newtons, and it had okay, I'm just going to say 10 joules of energy. Then if we wanted to find the height, then the force is 2,700. The height is the energy is 10, and the height in meters. We would rearrange our d equals e or e equals f times d to make d equals e over f. 10 over 270, 1 over 270, whatever that number is, it would be very small. So I don't think those were the numbers. It might have been the other way around. When work is done against frictional forces, then there's a temperature increase of the object. Okay, so any frictional forces, which is the movement of any surface or any particle over another particle. You can get friction in pumps as well. So as air is moving over other particles of air, then there will be friction, and so therefore an increase in thermal energy store. Here are your questions. And the answers. Okay, so we've talked a lot about energy, but energy isn't actually that useful. So if I said I was going to give you £1,000,000, you'd be very happy. If I said that I was going to give it £1,000,000 at the rate of £1 every 100 years, you'd be less happy with that because it would take you many hundreds of years, or 100 million years, in fact, to get your £1,000,000. Power is the rate at which energy is transferred. And remember, rate is just something divided by time, the amount of a thing happening in a unit of time, how quickly something is happening. Power is measured in joules per second, and that is the watt. So here's an example of what that might look like in physics speak. An object which transfers energy does so at a certain rate. The metal filament in this light bulb transfers the electrical energy stored into heat and light. This bulb transfers 2,400 joules of energy in 60 seconds. To find power, you can use the equation P equals E divided by T. There are two other equations, P equals I times V and P equals I squared R, but they are in the electricity topic, and there is a video where I explain how actually the amount of current and the amount of voltage does give us the amount of energy per second, because current is the amount of coulombs per second and voltage the amount of energy per coulomb. So the amount of energy per coulomb per second gives us the amount of power per second, the amount of power. Here's an example of some mechanical power. Power equals work done divided by time. We've got a 2,000 kilogram container, and it can be taken to a height of 5.4 meters in 30 seconds. 30 seconds. Find the power of the crane. Work done equals force times distance, so that's 2,000 newtons times 5.4, giving me 108,000 joules. It took 30 seconds, so we've got the energy, which is what this equation is for, energy, work done, force times distance, divided by the time, giving me the power of the crane is 3,600 watts. So whenever you've got to do a power equation, you've got to figure out what the energy is and then divide that by the total time. Reminder about efficiency. Efficiency is not just the efficiency of energy, it can also be the efficiency of power. And this is a megawatt. Remember, mega means a million. So a megabyte contains a million bytes. A megawatt contains a million watts. Here are your questions. Oh, sorry, before we go on to the questions, rabbit, pink pen, eyeliner. Eyeliner. Rabbit, pink pen, eyeliner. What? They're your passwords. Eyeliner. And your answers. All right, thank you very much, everybody. I hope you have at least learned something. If not, enjoyed these videos. Any questions, just send me an email.